All right, let's start. My name's Giuseppe. I love Flutter and AI, and so I was thinking I'm going to combine both in my talk to make the best strategy game ever on our phones. So I've been working with Flutter since 2020, and I started my master's in AI last year in Zurich. And I'm going to start with the demo of what we're going to build. It's, okay, I have to switch here. Yeah. It's rock, paper, scissors. So this runs completely offline. Like you can see, I've got airplane mode on, and I can do the gestures, and then it will recognize and play against the computer. So yeah, it's pretty cool. It doesn't work all the time, but now it works pretty well. Yeah, and I can do all the rock, paper, scissors gestures, and it will map them, like, yeah, and do the logic against the bot, which just picks random moves. So, okay. And since this is a Flutter conference, I wanted to start with a basic intro to machine learning, since everybody talks about it, and we'll quickly work to CNNs, so convolutional neural networks, which is the kind of model I'm using in this app to run the inference. And I won't go too deep into the technical details or math, but just give you visualizations and intuition to understand everything, how ML models work. So people tend to mix up AI and ML all the time. So ML is a subset of AI. Like in AI, there's lots of other interesting things like symbolic reasoning or planning, but yeah, we're just going to focus on the machine learning part, and it's defined as like taking data and making machines learn from it. Oh, I don't have my slides on. That's great. Okay. And you don't explicitly program 1,000 if statements or something. You just program an architecture which has trainable parameters, and then you learn these from the data. So that's the learning part, setting these parameters automatically from the data. And the three kinds of machine learning problems you have are, unsupervised learning. That's when you have unlabeled data. So this is used for things like clustering. For example, when Cloudflare blocks you from accessing a website, it's probably because they detected that your traffic looks like an anomaly. So it would be like a point somewhere out here which does not look like the normal distribution. Then there's supervised learning, which is when you have labeled data. So here you want to predict the label. For example, if I give you a new point, which is here, you would say, okay, it's probably the blue class. And then there's reinforcement learning, where you have an agent which takes actions in an environment, and this changes the environment, and you get a reward from it. And this is mostly used for games like playing Atari games or Pac-Man or stuff like that. So we're going to focus on supervised learning because we do have labels. So we have images, that's the input data, and we want to predict the labels. So whether I'm showing rock, papers, or scissors. And this is where deep learning also happens most of the times. That just means you have a model with a big number of parameters, and you let the data speak for itself as much as possible. So let's start with a very simple model for machine learning in supervised learning. So this is a multi-layer perceptron, and they're feed-forward neural networks. So you have the data, it goes in here. So for example, if you're trying to predict the price of houses, this could be like, what's the zip code, how many bedrooms does it have? So this is all the input data. And then there's a bunch of connections where you do weighted sums. So these weights are the parameters you're going to learn. And yeah, it just does the matrix vector product of the input data and the weights. And then it passes through a nonlinearity, and it just repeats a bunch of times. Yeah, and the nonlinearity here is a rectified linear unit. There's a bunch of others you can use. That's an implementation detail for us. So when you've trained a multi-layer perceptron, it takes the input features, and using the learned weights and the nonlinearities, it transforms them into a latent space or a hidden space. So here's your input data, and it transforms them from one layer to the other until in the end you're able to use a classifier or to just draw a line which separates the two classes. So here in the original feature space, you're not able to draw a line which clearly separates the classes, but after all these transformations through the hidden layers, it's very easy. And theoretically, if you have enough layers and neurons, you can express any function with an MLP. So let's look at this in practice. I just have to be able to switch this node. Okay, so this is an MLP running live in your browser. Here's the definition of it. You have two fully connected layers. That's what the FC here stands for, with 6 and 2 neurons, and this is the activation function or the nonlinearity. And so here's the input data which you're trying to classify. So you try to draw this boundary region. Let me just reset the data. So here, yeah, you can see live how the weights update and this boundary region shifts. So it's going to take some time for the gradient descent algorithm to update all the weights, but then maybe let's try some simple data. Yeah, it's a bit better here, a bit faster. And you can see how it transforms the space. So this is the original space, and then if you step through the layers, you get to the, like you can see how it distorts the space completely because of these nonlinear transforms. But in the end, you get to this kind of space where it's able to just draw a straight line here to separate the two classes. Okay. All right. Now, if we want to use MLPs for image data, we run into problems pretty quickly. Because, for example, this cute dog here has 128 by 128 pixels, then 3 channels again, so it's like 49,000 values for just one neuron. And that's way too many. Yeah, then times 64 neurons. If you have 64 neurons in your first layer, you would have 3 million weights just for that first layer, and that's too much. It doesn't work that well with image data. So we have to use a different idea, which is a convolutional neural network. And this is actually inspired from nature. So if you look at how we process visual data, it kind of works the same. Like lower neurons in your brain are able to recognize things like edges, and then this feeds into higher layer neurons, which do recognize things like eyes, for example. And so it's kind of like widgets in Flutter, where everything is composed of simpler things. And another advantage of using this approach is that these features can appear in different patches, and it's much easier for the network to learn what a dog is, for example, than if you were to use the MLP approach. So here you can see the difference between a fully connected layer on the left and a convolutional layer on the right. So here you have a connection with all of the previous pixels or neurons or whatever. While in a convolutional layer, you just look at small portions of the picture. Like for example here, you don't have to look at the whole picture to be able to say, okay, this is an eye or this is a nose. Yeah, so you need way less weights to learn a representation of the data. So let's look at what a convolution is. So you're trying to learn these filters, which is just a matrix. And when you apply a convolution, you slide it across the image and do the dot product, and then you get this convolved feature or activation map. Yeah, so let's look at a more practical example. What these kernels or filters, it's the same thing, what they can give you. So for example, I have this filter here, and yeah, imagine you have a big patch in an image which is the same color, it's gonna be just zeros, right? You add the same thing, you subtract, so yeah. What this is gonna give us is the edges, because it's only gonna have a value when the color changes. So yeah, if you convolve this kernel over this image, you get, yeah, you can basically see the edges. And then this next filter is a Gaussian blur. You can see it accentuates the center value, but like the outer values also bleed into it. So if you apply this a bunch of times, you get a blurred version of your input image. And now these kernels here are handcrafted. And with CNNs, we want the network to be able to learn these kernels for the data, like to be able to classify them or whatever you want to predict. So let's look at this simple CNN to distinguish two characters. Let's say you build 3 kernels or filters. The first one detects an edge, and these one detect corners. And now you can see here, this is the activation. So dark value means like higher activation. White values mean no activation, and you can see like the maximum is somewhere here because that's where the edges are. So yeah, when you threshold these values, for example, you set everything to 0, which is not higher than a threshold, you would end up with this. And then in this space, it's easy to say, okay, this must be a C, because only the C has 2 edges, while D has these hard corners. So in this space, you can very easily draw a line to distinguish between C's and D's. And so the cool thing about the CNNs are that it has an inductive bias, which is called translation invariance. And this makes a lot of sense when you have spatial data like images, which is where CNNs shine. So if you change the input data, like if you transform it, shift it, rotate it, it's not gonna bother the CNN that much, because like here you see if you shift the input image to the right, it doesn't really matter. Like it's still the same value here, it's just shifted as well. With an MLP, this wouldn't be the case. It would completely mess up. So now we're missing just one more ingredient. Before we can make more complicated feature detectors, we need a way to increase the number of pixels a layer looks at the deeper we go into the network. And we can do this through max pooling, which like kind of downsamples the data you have. So here you just take the maximum in a 2x2 grid. And what this does is that the deeper you go into the network, so this is a deeper layer. If you look at one of these neurons here, it's connected to these neurons through the kernel, and which in turn is connected to like almost the whole picture. And this makes sense when you think of it intuitively. Again, with the composition idea, like for example, this thing here detects edges, and this detects eyes, then the next one detects a whole face. And like the more complex your feature is, the more like the bigger the portion of the original image you have to look at is. Okay, so this is the architecture of some complicated CNN, and you can see how the dimensions are. Like the deeper you go into the network, the more complex the feature this layer is understanding is. And you can see also the max pooling, which downsamples the data. And then here, this part in the end, this is the classification head, which takes these values, which are very abstract features, which you can't really interpret, and then tries to basically draw a line between them to separate them, the classes you want to predict. Okay. Let's look at another CNN which runs live in the browser. Yeah. So this runs on like 28 by 28 pixels images. And here you can see the individual layers. Like the further you go, the deeper the layer is. And you can maybe see here, in the first layers, it looks like it kind of does the edges and stuff. And the deeper you go, the more downsample or the less resolution these features have, until in the end it's just 1 pixel, or a vector if you want. And then with this vector, you're able to linearly separate these classes. Yeah. And this runs live in your browser as well, which is pretty cool. Oops. I'm almost back there. I need my presenter notes. Okay. All right. Now I hope you got the intuition. Let's see how to train and evaluate these models. In this example, we have a regression problem. So given the x value, we want to predict the y value. And these blue dots are the samples or the data points we have. And these are sampled from this orange line with noise. And then we have a model which basically says, okay, this blue line is what generates these points. And it does pretty okay, I would say. And now you could think, oh, let's just add a bunch of layers and then the model will be able to be much smarter and stuff. But if you add too many, it overfits. It just draws a line through all these points, which is not what you want because they were sampled noisily. So we need a way to detect this when overfitting happens. And what we do for this is we split the data we have into a training and a test set, and then we look at how it performs on these sets. So the training set is just used for training, and the test set is used afterwards to evaluate the performance on unseen data, just to make sure that the model generalizes well. And you can see here, for example, like on the train set, this complex model does better, but on the test set, it does really bad. So this here is the better model. And the thing you can see here is the bias variance trade-off, which also kind of shows this problem again. Like the more complex you make a model, the higher your variance of the output data will be because you just have a bunch of parameters. But if you make it too simple, that's bad too, because what you want to minimize is the sum of both. So you want a low variance and low bias. So there is this kind of optimum model complexity for a problem, and the way you find this is again through the training test split, and yeah. Let's look now at how a model finds, like how can you find the parameters which are which we want to optimize. So here we have just 2 parameters for simplification, and we're going to use stochastic gradient descent. So basically, the idea is you start at some random point. So this is a combination of weights, and then you look at the loss landscape, which is drawn through these ISO lines here. So you want to minimize the loss. The loss is a metric which tells you how good is my model at predicting the data. And so you want to get to the point of minimum loss. So what you would do if you're on a mountain, you just go, and you want to get down to the valley, as fast as possible, you just go downhill. And that's what this does, basically. It calculates the gradients and then follows them. So you can see it goes orthogonally down the loss landscape to get to the valley. Trying to get to this point, but it doesn't quite get there for some reason. And that's because it gets stuck in a local minimum. Like you can imagine if you're in a valley, like, and you calculate the gradient, like there's no gradient. You're already, there's no downhill in a valley. You have to go back up and then down again, but yeah, it's stuck here. What you can also see is the learning rate here. Like in the beginning, you take bigger steps, and the closer you get, the smaller the steps or the smaller the learning rate gets. and you do this to minimize oscillations. Now the solution to getting out of the valley is to use momentum. You can kind of see this better in this animation. So the blue ball is without using momentum, and this ball is with using momentum. So here we get stuck in the local minimum. We're not able to find the best combination of parameters, but here we are. And there's a bunch of different other optimizers you can use, but this is the intuition. You have a loss function, which you take the gradient of with respect to the parameters, and then you use that to update the parameters. Okay, now it's time to see a little bit of Python code to see how this actually works. Okay. So what we're going to do is we're going to train an MLP and a CNN to classify these digits. Yeah, so it's 30 by 30 pixels, I think, and these are all handwritten digits. This is how we define an MLP using PyTorch, and yeah, it's basically just a linear layer, then this non-linearity, the rectified linear unit we saw in the beginning, and then it's again the same, and in the end you have this classification head, and it uses this softmax function to calculate the probabilities of all classes. So it makes sure that the class probabilities sum up to 1. A CNN is also pretty easy to define here. Yeah, you have this first convolutional layer, and you can define the size of the kernel, so the size of this image filter you want to learn. And then you have a second one, and then in the end, 2 fully connected layers again to do the classification. And here you can also see these pooling layers, which are after each nonlinearity to yeah, get this translation invariance. Now for training, here we use the stochastic gradient descent we talked about. You can see here, this is the learning rate and the momentum we have to use to not get stuck in local minima. And then you just get a subset of the data and calculate the loss, do backpropagation, and step towards the better set of parameters. Yeah, and then for the testing, it's more or less the same. Let's look at the results. So the MLP has 6,442 parameters, and you get an accuracy of 82%, which is pretty good in my opinion. But let's look what the CNN has, because it has the same number of parameters, so to make it more comparable. And this one gets an accuracy of 95%, which is a lot better. And that's, again, because it's spatial data we're dealing with here, and CNNs are just very good with spatial data. Okay, we did it. We're done with the machine learning part, almost. We're not going to build a model on our own. We're going to take an existing model and we'll fine-tune it, because otherwise you would have to wait for, I don't know, days, weeks to train your model if you want to do it from scratch. And also, I'm not smart enough to come up with all these great architectural ideas. So we're going to take the MobileNet v3 from Google, and the name implies already it's optimized for mobile devices. And then we're going to fine-tune it. So we're going to give it another data set separate from the one it was trained with to adapt it to our use case. And this is the data set we're going to use. It's called Hagrid, Hand Gesture Recognition Image Data Set. And it's perfect for our use case because it's a bunch of very diverse people in very different backgrounds and lighting conditions and so on, doing a bunch of hand gestures. It's perfect because that's what we want to predict, right? So Hagrid is like 700 gigabytes, and it also has information for bounding boxes and so on, which we don't care about. We just want to do the image classification. So there's a copy of it on Hugging Face with just like 3 gigabytes or something, and just prepared for the image classification part. And that's what we're going to use. So these are the gestures, and then we can map palm to paper, stop to paper, and so on, fist to walk. Yeah. So to fine-tune this pre-trained model, it's super easy. First, you define it. So basically, you get the model here from PyTorch. Then we have 19 classes, right? We have these 18 gestures, and then there's an additional class for no gesture. And then the only thing we have to change here is the classifier. So it's the very last part, the very last layers, the classification head of the network. And here we just add a bunch of linear layers, and yeah, these non-linearities we saw before. That's it. We're done defining the model. Then the training is kind of the same as I showed you before in the notebook. And doing this, we train it for 20 epochs, which takes like 8 hours. And then we get a result of 98% accuracy, which is really good, in my opinion. So now we just have to integrate it into Flutter. Yeah, we have to convert it to TF Lite first, because that's the library we're going to use to run it on the device. And it's just these 2 lines in Python. Then you add that to your assets, as well as adding TF Lite Flutter to your pub spec. And then you can use this isolate, this interpreter, give it your asset with your model, and create this isolate interpreter, which is, isolates, it takes work off the main thread, which is, it takes some time to run these models, so better to do it on an isolate. And now we have to pre-process our data. So we get an image file, read the bytes, resize it to 300 by 300, because that's the shape that the network expects your inputs to be in. We have to do one more thing. We have to normalize it. So we have to normalize the pixel values to be between 0 and 1, because again, that's the way the network was trained. So it expects the same kind of input. Now we have to rearrange some pixels. So usually you have them from layered as height by width by channel. So for each pixel, you have first the red, then the green, then the blue value, then again red, green, blue. But that's not the way the network expects the data to be in. We want all the red values and all the green values, then all the blue values. So we have to do some rearranging of pixels. But then we're almost done. We have to add one more, we have to reshape it again. We have to add this extra dimension, which is the batch size, because you could use this to classify multiple images at once. But we're just going to say the batch size is 1, because we just want to classify one image at a time. And yeah, that's it. Then we can run the isolate interpreter with our input tensor, which contains our preprocessed data. And it's going to write the results into this output tensor, which is just a list of 19 values, basically. And then we just get and this represents the class, the probabilities of each class, so of the different gestures. That's it. Then we just get the one with the highest value. And that's our prediction. Cool. I have some more tips and tricks for you. You can use Netron, which is a neat app to visualize ML models. If you have them as TF Lite, you can drag and drop them in there, and then you can visualize the shapes, what's going on in these layers, and so on. Then another tip is to check that the output tensors in your Flutter implementation do the same as when you run them with Python to find out errors in preprocessing. Because when I developed this, I had, for example, the pixel order that was a nightmare to debug. And then, run your inference on a separate isolate to not block up the UI thread. If you want to perform some performance optimizations, you can do pruning, which is removing parts of the network which are not as important. Quantization, which means using, instead of using float values for the weights, you use just, 8 bits or something to make the model smaller. Then there's a different, like I used MobileNet v3 large. There's also MobileNet v3 small, which is less accurate but faster. And then another idea is if your accuracy is not very good, just average the output. Okay, we did it. But why stop at rock, paper, scissors, like the basic version? Maybe you know this. Oh, there's no sound, but yeah, it's rock, paper, scissors, lizard, Spock. And I did that as well, so let me just get it on here. So this flash button up here is actually how you enable lizard and Spock. So if I do this sign, it's gonna be Spock, and I lost because paper disproves Spock. Okay, let me try lizard. Again, I lost. This computer is just way too good. Well, yeah, you can download the APK later to try it out. I'll link it. But actually, why stop at 5 gestures? I mean, we have the technology to do more. There's a rock, paper, scissors 25. It just dropped. Yeah, I love this game. But there's even more. There's rock, paper, scissors 101. It's the perfect game because there's just a 0.99% chance of there being a tie. So also the interactions are pretty cool. For example, alien terraformers mountain. Yeah, you should check it out. And the way you could implement this is to use another kind of model, which gives you these hand landmarks. So these are 21 points in space, and then you can use that to define custom gestures. So for example, I found this project here on GitHub where you're able to say, okay, if the finger is curled like this, that's another gesture, and so on. Like, yeah, you could use this to build something, and you can see it runs in real time. So if you want to implement rock, paper, scissors 101, please do so. Yeah, that's it.